In this week's engineering tips, we're discussing the use of max material condition and least material condition to help determine our dimensions and tolerances. Let's get into it. In this week's engineering tips, we're going to discuss the use of max material condition and least material condition to determine nominal dimensions and tolerances. This week's video comes from a comment from Dave on YouTube, who asked when to use max material condition and least material condition versus just standard tolerance forms. If you haven't seen our previous video, the link to it is in the description below. Max material condition and least material condition are two size designations typically used in GD&T pertaining to bonus tolerance. However, we can apply the concepts of max material condition and least material condition to the mating interface between two components to help determine nominal dimensions and tolerances for a specific component feature. Let's have a look at an example problem to demonstrate this method. Here, we have a simple scenario where a purchased dowel pin is press fit into a plate. The dowel pin in our example is a purchased pin from McMaster-Carr, who provides the associated dimension and tolerances with said pin. However, as the designer, the question still remains, what should be the size and tolerance of the hole in the plate? The dowel pin spec sheet provides both the nominal outside diameter and the tolerance of the pin. Here, the pin has a nominal diameter of 1/2 inch, with a tolerance of plus 1/10,000 to plus 3/10,000. Using a tolerance stack-up table like the one shown, we can enter the dowel pin nominal outside diameter and tolerance here. To maintain the press fit at all times, we need to have an interference fit at least material condition for the mating interface between the pin and the hole in the plate. Let's start with setting the minimum interference fit to be 1/2,000 at least material condition. We do this by entering a negative 0.0005 here in our tolerance table. Next, we must determine the maximum allowable press fit at max material condition at the pin to hole interface. Prior analysis using FEA indicates that 3.5 thousandths would be the maximum allowable interference fit between the pin and the plate based upon our specific application. Therefore, we put negative 0.0035 in the table here in the cell associated with max material condition of the interface between the pin and the plate. With the interference fit at max material condition and least material condition determined, we can now solve for the maximum and minimum allowable size of the hole in the plate. The smallest the hole can be, max material condition, to satisfy the interface requirement at max material condition is 0.4968 inches. Likewise, the largest the hole can be to satisfy the interface requirement at least material condition is 0.4996 inches. These two values here represent the required size of the hole at its own max material condition and least material condition. We could add these two values to the design drawing directly by way of limit tolerancing. Alternatively, the allowable hole size could be expressed as a nominal with a bilateral tolerance. Or, the hole size could be expressed as a nominal with a symmetric tolerance as shown here. While max material condition and least material condition are typically used in GD&T for bonus tolerance of a specific feature of size, we have seen here that the use of the concepts of max material condition and least material condition can be used to determine the feature tolerances themselves. A common approach seen often is to prescribe an initial nominal dimension and tolerance, then subsequently revise both based on the interface requirements. However, the approach demonstrated here using max material condition and least material condition effectively encourages one to work backwards by focusing on the interface limits first and then the applicable feature tolerances second. Thanks for watching. If there are any questions or anything you would like to see, feel free to contact us or drop a comment below. Don't forget to like, follow, and subscribe to get more engineering tips.